Catalysts. Now, before we get into the specifics of the catalyst, I just want to give you a few examples of environmentally draining and damaging industrial processes, and then we'll segue into the specifics of catalysts. So iron or even petroleum refineries, they can be very damaging to the environment. And let's even steel mills, okay, are bad for the environment. And have tough government regulations compared to others, because nitrogen, carbon, and sulfur oxides are detrimental, especially. So an example of a sulfur oxide, let's say we have sulfur trioxide here. If this gets released into the environment, very, very dangerous. For example, if we look at this equation, as we can see here, if an SO2 gaseous adds with an oxygen that is gaseous, it can create SO3. And this SO3 is what I've been talking about here. It's an exothermic reaction. And like I said, SO3, along with these other oxides, very damaging to the environment. However, when we create SO3, this is a valuable product. And in order to increase production of this SO3, the higher the yield at a faster rate is obviously preferred. What do we use? We use a catalyst, vanadium oxide, vanadium 5 oxide here, and it helps increase the rate of the reaction. Now, it can increase it in the forward direction, but it can also increase it in the reverse direction as well, which is unfavorable. So, if we were to draw this out and look at A, drawing a labeled potential energy diagram, and let's put our reactants in. We have our SO2 and our oxygen. And as you saw in the previous video, that the reactants hit here at the activated potential, or the activation complex. They should be here as well because it could go backwards or it could go forward. Let's assume it does go forward and it proceeds. As you can see, the products will eventually form. Then you have your SO3. This is a labeled potential energy diagram. We have your reactants over here, so this will be your R. This here will be your products. And then of course, the difference between the potential energy, right, because potential energy is always on the side here on the y-axis, and then reaction progress is on the bottom. If you were to get the potential energy of the reactants right over here, right, this is the reactants, and then the potential energy of the product, you find the difference between that. This is going to be your delta H, or your delta HR, your enthalpy, your release of energy, change in energy. So this is pretty much A. What are we going to do for B? Use collision theory to explain why the rates of the forward and reverse reactions increase. So if I were to use a different color, this here would represent a catalyst. So if I were to pinpoint that, this would be your V2O5. It's this V2O5 that allows this reaction to proceed and not have to hit a high activated complex here, but a lower amount here, because it has the binding sites for these reactants to get on and therefore allow the progress reaction to happen a lot more efficiently, a lot faster, where less amount of sufficient energy needs to cross this barrier here. This would be your catalyst involved, your V2O5. Now why is this important, this V2O5? Because it leads to the next question for C. How does this catalyst over here affect the delta H forward, so the enthalpy change forward reaction, and the delta H of the reverse reaction? Well, where is the delta H of the forward reaction? It's going to be this area over here. And how about the delta H of the reverse? It's going to be this area over here. Why is this the case? Because the delta H is going to be always a difference between the potential energy of the reactants potential energy of the products. How do I know that this delta H forward deals with this reactant? And how do I know that this delta H rev deals with this one, this potential energy of the product? Because whenever we deal with forward, it's always going to be in relation to the activated complex and the reactant. However, this one over here, the reverse, it's always between, again, the activated complex, but with the product this time. So let's go back to the forward reaction. This is your reactant, and again, always reference it to the activated complex, this one over here. So you find the difference between that. This here is going to be your activation energy of the forward reaction. So the forward relates to the reactant in question. Similarly, for the reverse reaction, it's going to be, again, same thing with the activated complex, but with the in relation to the product. So the difference between that. So that is going to be your activation energy of the reverse reaction in relation to the product. Hence why, when we look at the delta H between both of these, right, we have the delta H metric between the reactant and between the product. How does this catalyst affect that? Well, it doesn't matter how small this catalyst is. This catalyst could be this small or even smaller than that. It does not matter. What do we see happen with the potential energy of the reactant? Nothing. It's still going to be here. It doesn't matter what happens in the green. The V2O5 does not affect that in any way. How about for the product? That also doesn't change. The delta H for the product doesn't change either. So this will always be the same, right? So this one over here, this is never going to change regardless of how the catalyst affects the reaction. So I guess for C, how would we answer C? It doesn't affect. Okay. So to finish off B, use collision theory to explain why the rates of the forward and reverse reaction increase when the catalyst vanadium 5 oxide is present. Well, remember there would be a decreased amount of sufficient energy needed to cross the activated complex barrier and the molecular geometry orientation. Remember, both of these must be met in order for the reaction to proceed. So again, for this, if you have no idea what this means, go see my previous videos on activation energy and potential energy and collision theory for clarification on this. Link is in the description. Therefore, so based on the example that we just looked at, I can also add here for catalysts only involve in the decrease of activation energy. They're also very useful in industrial processes. To do reactions in environmentally favorable conditions. Environmental, okay, for over here, abbreviated, in environmentally favorable conditions. Where high temperature, for example, isn't necessary. Now we did look at that previous example for the SO2, so we can just reference that. Or another example could be within our bodies. Even in the human body, enzymes are always involved since reactions must take place at around 37 degrees Celsius. Now, with things like cellular respiration, these are very exothermic reactions. And obviously within our body, temperature is not very high. It's again at 37 degrees Celsius. So how is it possible that these extremely combustible and high energy release reactions, how can they occur every single second, every single millisecond within the human body without harming ourselves internally? It's because these enzymes are involved in catalysts, or enzymes too. So it just helps to ensure that the process is broken down in steps and it is allowed to undergo and proceed for the reaction, as opposed to the reaction not occurring and going in the backwards direction. So we looked at the SO3 product being formed example using V2O5 as the catalyst. We can now use another reaction producing ammonia, nitrogen trihydride, but we're going to use a catalyst, and this time the catalyst is going to be K2O, right, or potassium oxide. Obviously we have to balance this out appropriately, so just quickly balance it. There we go. Why this ammonia is very important is because fertilizers or explosives require this. Okay, so this is why this is extremely important. Now, it is important that we yield NH3 quickly, as opposed to an increased temperature, which is long process, and this can actually reverse the reaction. So rather than putting this here, I'm actually going to put in the other direction as well. It can actually go backwards. So if we have, like I said, an increase in temperature, can be a long process. Okay? This long process is not necessarily very good, because even though you can get more of the NH3, it can also go backwards in the opposite direction and create more of your reactant as well. So it's kind of in a teeter-totter approach. It goes back and forth, back and forth. We don't want that though. We just want to create a lot of the NH3 and then cut it short. So rather than having an increase of temperature, again, which can be a long, arduous process for it to reach that particular temperature, and during that reaction process, it's going to take a long time, it could go backwards, which isn't going to be yielding our efficient results. So how do we have a high amount? Very, very quickly, we use a catalyst. So the reactants, these ones, bind on to the K2O so that the reaction can proceed in this direction. And then once we have a certain amount of NH3, a good amount of yield, we cut it off so that we're just left with just our NH3. And then we just be able to extract that, and then that's going to be a lot more beneficial to have. This would be known as Haber and Bosch. Now another example that we use in our everyday lives is paper. So we get fiber from a particular area of a plant, right, as opposed to the other fibers. So we get the particular fiber, and then we get it and we compress it. And we compress it into these thin sheets, and within that process we got to dry them out. Once they're all dried, it's going to give us a brownish color. Again, kind of looks like paper, but obviously in order to write things with our utensils, with our lead pencils, it's a lot better to have a white piece of paper where it's very light, so you can kind of see it easier as you're writing. So we're going to add bleach, and this is going to be a chlorine-based bleach. This decreases the brown color, decreases brown, and obviously it's going to increase white. Now, having a lot of the bleach can be quite harmful, because once that bleach is treated and treats this, it's going to go obviously into the water, and then it's going to go out into the environment, and this is not environmentally friendly. So we actually add xylanase. And why is this important? Because xylanase decreases the amount of chlorine bleach needed. So we still need to add chlorine bleach to decrease the brown and increase a white color, but for environmental safety, this xylanase decreases the total amount of chlorine that is needed, so we don't need to add so much of it. So you still end up getting your white product of the paper, you just don't require so much of this chemical product within that process. Now, we also got to worry not just about the utensils of the lead pencil writing on it to be able to see it, but we also need to erase. And if we erase things, it needs to be a strong, rigid, firm piece of material. So we add amylase as well. Add amylase. Now, you should be quite familiar with salivary amylase. It helps digest starch. Okay, it's within the first chemical digestive process in biology when you consume particular food, especially if it's high in carbohydrates. Now, when we add this amylase, this can actually produce starch as well. It doesn't just break it down like salivary amylase. Other types of amylase can actually produce starch as well, so can produce starch. Now, why is this important? Because adding starch into this piece of paper that we have there increases strength. And this increased strength, this increase of rigidity, will be able to withstand erasing against the surface of it. Now, these are the two green questions of the day. However, I do want to expand a little bit more on this question before I leave this to you on your own. So, this reaction, X is gaseous state, Y gaseous state, produces a Z, which is solid state, occurs only at very high temperatures. Of the factors that affect the rate of reaction, which one would you expect to be the most effective in increasing the rates of reaction? And in case you're still confused, I would ask you to see my video on, again, collision theory and rates of reaction. Again, they will be posted in the links in the description. Would like you to watch those videos prior to answering this question. I just want to quickly write out for you as a quick review, or maybe you can pause the video and remember what those different types of factors that affect the rates of reaction are. So I'll give you a couple of seconds to kind of think about that, and then I'll write them down for you. Alright, the first one was reactivity. Okay, and when we talked about the reactivity, remember, it was based on the total amount of bonds. So if there's more bonds, more or less bonds, they may or may not be more reactive or not, as well as stronger bonds. Okay, so brush up on what these were in that video for collision theory. Next, another factor that affects the rate was, hopefully you remember, ionization energy. And remember, for ionization energy, you could have a high ionization energy as well as a low electron affinity versus a low ionization energy and a high electron affinity. Another one that we looked at was temperature. Okay, if you have a high temperature, how does that affect the rate? Versus if you have a low temperature, How does that affect the rate? We're almost there. Then we had concentration. Similarity, if you had a high concentration, how did that affect it? Versus a low concentration, how did that affect? Second last one is the surface area. Same thing, high surface area versus low surface area. And the last one was a catalyst. Add catalyst, how does that affect? Or no catalyst, how does that affect? So out of these 6 factors that affect the rates of reaction, which ones or which one do you think would you expect to be the most effective in increasing the rate of reaction for this particular question? So like I said, these are the 2 green questions of the day. Use these 6 to help you answer this question, and then this will be the second green question of the day. Give this a try as well. This one, however, would require you to do a little bit of research online of this Haber Bosch process to answer this question. So a little bit of explorative learning. So I'm going to give you an opportunity to pause the video, try it yourself, and I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question.